person. They look pretty good. There's a little creative stuff that's bordering on.
I like how I'm wait,
You haven't gotten to the last problem yet, so just wait. You're in our retreat.
Okay, yeah, I heard I got some interesting things in the last problem. So we'll get there. So we're using everything we've learned, and we're going to try and make predictions using statistics. And so I'll go over a couple of things we're going to do today. So I was in between soccer games this weekend. I was reading. I found a copy of USA Today, and inside was on the cover was some statistics that just caught my attention. And it said, I think I didn't get the wording right. 69% of drivers get pissed off by other drivers who are on their cell phones. It's something like that. The dog pissed off. It was 69%. I was like, oh, where'd you get this data? I looked it up and I found the data. It's like, oh, okay, well, we can play with that. So just kind of curious with you guys, how many of you get pissed off when you see somebody else messing with their cell phone while they're in class or driving down the street? Raise your hand if that pisses you off.
For me, it's the blink.
4 of us get annoyed by that.
It depends if they have kids in the car.
That pisses you off more.
I
think it depends on if I have kids in the car.
Yeah, if they have children in the car, then I get a little upset because I'm like, it's not just your life, but if you just want to kill yourself, like whatever, I don't care.
Yeah, but if they're talking on their phone and then like they have kids, like I have a 15-passenger van, so if you want to talk on your phone and hit me, good luck. Like.
Okay, all right, so I don't know if we can actually do this. So let's see, are we going to go with 4 out of 8?
Sure.
Or get pissed off when other people use their cell phones. So you kind of do. I'm going to turn kind of into yes. So I think that makes it now 6 out of 8 of us, let's say.
I do it all the time, so I can't really. That's kind of critical. I'll point it out like I notice when somebody's on their phone, but
I swear I almost get hit at least 4 times a day by someone who's on their phone.
My car, like,
or cut off,
or
because they just don't see you.
Yeah.
And that's why it drives me insane.
It only bugs me. I get really mad when people don't use their blinker.
That's
really irritating.
Yeah.
I'd be like, are you turning it on?
Yeah.
Yeah.
That was a better question.
Actually, no, it makes me really mad. It's when I limited from you'll get mad.
Okay, we start off quite a discussion.
Past one person, there's someone in front of them going,
Oh my
That's
gosh.
always easy to send off in some
That's
bizarre
so
direction.
great.
Okay, so let's get back here. So 6 out of 8 of us. So 6 out of 8 is what percent? 75%. Excellent. When we make an estimate of a percent based on a sample like that, that's what we call a point estimate. So point estimate for all people we found by taking what I'm going to call X, the number of people who were annoyed, dividing by the total number of people, N. So we're going to get 6 out of 8 as a fraction, which could be reduced, but so what? We're going to call it 75%. And that is usually referred to as P for percent or proportion with a little hat over the top. The hat means you made an estimate. Okay. The actual proportion is P, and we don't know that because we have not surveyed all people, or all drivers, let's say. Because the poll was referring to other drivers. So that's what we call P hat. So we are estimating P. So for all people, change color. So P, there we go, is the percent of all people. In my demographic. We get a little sample, 6 out of 8, 75%. Point estimate. So that's one way to estimate a population parameter. Well, just before I continue with this, what other things might we want to predict about a population? Well, big popular thing is what percent of people feel this way, feel that way, look this way, look that way. So proportions or percentages are one big thing. So just let's make a note. Things we estimate about populations. We're starting off with proportions or percentages. So other examples would be, I could say, well, what's the percentage of women that attend BMCC? What percent of people at the college live in Hermiston? Maybe bright ideas of things we could estimate as a percent of a population.
Eye color.
Eye color, yeah, what percent of people have brown eyes or blue eyes or green eyes? So there's lots of things we can come up with percentages for. Other things we might estimate about a population besides percentages of people that, or things that fit a certain characteristic.
Cars.
That?
Who has cars?
Okay, well that would be a percent. So besides percentages, portions of people who have cars, who don't, or green eyes, who don't.
Maybe a ratio, would that count?
A ratio?
Yeah.
Like, what do you mean a ratio?
Who has cars to trucks?
Yeah.
Like who
That-
drives
so-
a car versus a truck?
Okay, so that'd be the same idea. Driving car versus truck. Truck is still a percentage, a ratio, proportion.
Then what are you asking?
What other kinds of things about a population might we want to estimate or know about?
Total size of the population.
Size of its population, okay, so that's one, yeah. Wasn't thinking of that, but that's good. I'm not really going to address that in this class, but that's okay. What else? Let's see. How about, we were playing around with information from sports teams like the Timbers or the Thorns in particular, like the height of people, the height of people in general, height of people in soccer teams. Okay. In which case, we are often looking at average height. Right? If we're talking about things that we think are normally distributed, what two things do we need to know to develop a normal distribution? Two things to describe a normal distribution. Right? Yeah, mean, standard deviation. Yeah, so a big thing that we're going to want to know about is if we think some data might be normally distributed or not, we might want to know the mean of that population. And along with mean goes the idea of spread. We want to know how spread out a particular population is. So we also might want to know standard deviation. So we, in particular, are going to focus on number one here, proportions and percentages in populations, and number three, means of populations. So in chapters 7 and 8, we're going to pick on proportions and means. If we had time for another statistics course, we would play with standard deviations, how to estimate standard deviation of a population. So this is, by the way, 7.2 is estimating proportions, and 7.4 and 7.3 too, but we're going to skip 7.3, is about means.
Why are we skipping 7.3?
I will explain that on Wednesday. That's okay?
Okay.
Why are we skipping 7.3? Yeah, it turns out to be not a useful skill.
Okay.
What's in 7.3? And I will explain why when we start 7.4. And we just don't have time to do standard deviation, which is cool stuff too. So let's get back to proportions. We just made an estimate of a population proportion. We said p hat is 75%. And this is our estimate You missed this fun part, Michael. Of the percent of people who are annoyed by drivers who use their cell phones.
What did I miss?
Our calculation of that 75%.
No, did you have it in hand?
Yeah.
Does it annoy you when people talk about writing?
Only in the city. Two ends. You're good.
That was a good math joke.
It is, isn't it? I said that.
Oh, I thought you made it up. I was looking at what I was writing.
Oh,
She
shit.
turns to me and she goes, "N squared," and I was like, "You made that up?" I didn't.
No, I wouldn't.
Okay. So that was our estimate. So now here's the question though. How good of an estimate is it?
Well, you got a
Small
pretty
population.
small sample.
Okay, I have a pretty small sample size, and that probably limits its goodness. What else?
Goodness is a word.
It absolutely
Oh, it
is in
is.
math. Yeah,
Okay.
it is. Especially a big word in statistics.
If greatness was what it was.
Sure. So what else is so? Okay, so I have a small sample size. That's a problem. What else is a problem?
We're around a similar age range.
You're on a
So it's
similar
not
age
very-
range.
We are.
What kind of sample did I just take? Was it a random sample?
No.
No, it's not a random sample. What do we call this kind of sample?
Convenience.
Convenience. It's a convenience sample. Who knows what kind of bias there is here? So okay, so I have a pretty crappy sample. Not that you guys are crappy. You're wonderful. But as far as a random sample goes, I don't have one. Okay, and it's a small sample size. But we're going to go with it anyway, just for fun. So one way of talking about how good an estimate is to talk about margins of error. How good is our estimate of 75%? And there's a couple of things we have to throw in to do that. So we started off with, I had a sample that started off with 8 people. I found that X equals 6 of them were annoyed. And X over N gives us what I call P hat. And that is our 75%.
Were you in this?
Yes,
Oh, I was gonna say.
I get to play on this one. Okay. Along with, and so often I'm using percent here, but a lot of times they'll talk about proportions not as percents. So often it'll be referred to as 0.75 instead of 75%. So often they're referred to as population proportions. I'm going to do that here, population proportion. 0.75 is the portion of the population I believe is annoyed by drivers who use their phones while driving. Now, in order to make a margin of error, I need what's called a confidence level. Confidence level. So confidence level is needed to find the margin of error. And what happens is the higher your confidence level is, the wider your margin of error is. If you want to be 95% confident that you have a good estimate, then you're going to have to widen what is acceptable for a margin of error, the space around your point estimate. So how confident do we want to be? 90%, 95%? 50%, right? 50% would be great. Yeah, so it's kind of wishy-washy, but it would give us a narrower margin of error. But I'm going to go with 90. Maybe we'll try 50 out. So I'm going to go with a confidence level. Usually I call that CL of 90%. So I'm just going to draw a little picture of what I think I'm aiming at. So I want to make an interval with a center. My center is what I call p hat. And I want to find a margin of error. So the margin of error is the distance to either side. So that's going to be plus my error to that side and minus my error to this side once I establish my margin of error. That gives me these boundaries here. My confidence level is the probability of being in between those boundaries. All right, we've done problems like this, right, haven't we? Mm-hmm. Okay. So what I need you to do is help me. Like if I put 0 in the middle, I'm probably doing z-scores, right? So I want to know what z-score would I pick so that I have a 90% confidence interval where that 90% is centered in the middle. So then the question is, well, how much is going to be in each tail? There's 90% in the middle. How much does each tail get?
5.
5% for each tail, right? So if we take our confidence level and we subtract it from 1, that gives a number that's called alpha. And you may have read about alpha if you read the book in section 6.4 and 6.5. And we want to take alpha and divide it by 2 to get my 5% in each tail. So what command am I going to use on the calculator to change a percentage into a z-score? Inverse norm. Is that what it's called on the computer too? Norm.inverse, right? Okay, there you go. Yeah, so what I want to do is, and I'm going to pick on the left tail. So if I pick on the left tail, now does the inverse norm work with left tails, right tails, or intervals? Do you remember? Left tails only. So here's a left tail right there. So I could apply the inverse norm or norm.inverse. So everybody give this a try with your calculating device. My percentage in this case is 5%, which the calculator wants as a decimal. And I like to tell it my mean and standard deviation. And I forgot my cheat sheet for Excel. Is it the same order on Excel?
It's norm.inv.
Oh, you got to read it.
Yeah, you want to.
Probability mean.
Okay, yeah, same format on the on Excel. So on Excel, so norm.inverse 0.05, comma 0, comma 1. And since we're to the left of 0, we should get a negative z-score on that side. Anybody get it?
Negative 1.64.
Negative 1.64. Jason, enough? Okay, and then did you write this problem down? Or yeah, I got the illustration. Go ahead. All right. So what if I wanted to calculate the right side instead? Any thoughts on that? Just change the sign to be positive 1.64. If I was going to use the inverse norm, what probability would I give it?
1 minus that?
1 minus the 0.05 because that's in the other tail. Yeah, so I give it 95%. So just check for fun. What happens if you give the inverse norm function 95%? With a mean of 0 and a standard deviation of 1, we should find it's the opposite of what we got. Oops, 0 and 1. Thank you.
It's the same thing as the negative.
Okay, excellent. That's what we want to know. So usually the one on the left's easier to go for right away. You just find your alpha by subtracting the confidence level, cut it in half, and that's the probability you use. All right, so we're getting closer to calculating a margin of error. So we found what I call the critical z-score. The next thing we need to do is change that z-score into a percent of the population. Because we're saying my p hat is right in the middle. That's my 75%. So we have to figure out how to change a z-score of 1.64 into a percentage of the population. Now, well, if 75% is in the middle, it's going to be something bigger than 75 on one side, something smaller than 75 on the other. Agreed? Okay. So I'm not going to go through the algebra of how that happens. I'm just going to give you the formula from there. the way to change the z-score into a proportion, like p hat, is the following. You want to add on the right side to p hat, that z-score, which is called z sub alpha over 2. So for us, we're going to have our center is 0.75. We're going to add on to that 1.64 times, then you take p hat times q hat, divide by n, and take its square root.
0.75 times 0.25
Yep.
over
8 people.
8 equals.
Yeah. So I would take my 0.75 times 1 minus that is 0.25, divide by 8. And so that will give me the right boundary. This whole thing right here is what I call the margin of error. And we usually just give it the symbol E. So this thing right here is what I call E, big E. Biggie, biggie, biggie. All right, let's calculate that sucker.
Now this is just for the left side, right?
Yeah, we would do
Obviously-
this. This is for the right side. Subtract and you get the left side. Yeah, so this is going to give me the right side. So generally what we do is we write, I would usually write plus or minus, plus or minus. So I'm going to repeat it with a minus. That'll give me the left side. So the plus takes me to the right. And the minus takes me to the left.
And it will take you from the center to
From the
right
center,
boundary,
what's that?
to the right boundary.
Yes. Takes me from the center to the right, from the center to the left.
So
That's why I'm adding and subtracting from p hat.
will it give you?
I'll just wait. Yeah, so let me do that. So I'm just going to calculate E for a minute. So if I take my 1.64 times the square root of 0.75 times 0.25 divided by 8, I get a margin of error of about 25%, 0.25. That's a pretty darn big margin of error. Agreed?
Yeah, it's about a quarter.
Yeah, it's huge. Oops, I'll repeat that. So I just calculated that E is about 0.251. So if I go back to my picture here, I've said E is about 0.25, so that means I want to jump this way, 0.75 plus 0.25, which is over 100%. I want to subtract going the other way, which is going to put me on this side at 49.9. You guys getting about those numbers? So what I'm finding, oops, over there, there.
Thank you, everybody.
There we go. So p hat, that's my 0.75, plus z sub alpha over 2, that's my 1.64. And then I have to take the square root of 0.75 times 0.25 over 5 over. And I calculated, let's see, I didn't calculate that part separately, darn it.
Well, add what one body what we got.
Hang on a second. Okay, 0.153-ish. What's that, Michael?
No.
And cleaning that up and rounding it a little, I get that's about 0.251. And so I get that on the right side, I get 0.01. 0.101, excuse me, for the right number. On the left side, I'm just going to subtract that.
What?
If you add these, ooh, shit, I put that in the wrong spot. 1.01.
Yeah. 1.0. That's right.
1.001. Okay, that is right. 1.001. All right, And then on the left side, I'm going to do a minus with that. And help me out so I don't screw that up. That's going to be 0.4901. Oh no, 491.
0.491. Or 499.
That's right.
And then minus this one.
No, that's it. 0.75 minus the 0.251 is 0.499, right?
The left boundary was 49.9.
Yes, that's 49.9% right there.
You hadn't subtracted it, had you?
So this left number comes from taking the 0.75 and subtracting the 0.251. If you take 0.75, subtract 0.251, you get 0.499. That's the combination of those two. That's, ooh, shit. That's what we call the error. Is anyone not getting roughly 0.499? Who's not getting it? You're not getting it, Jeremy?
Well, I'm not following up, so yeah.
Okay. So, do you want me to show you how to do it on Excel? We'll look at that. Not a cute spreadsheet?
We don't need to.
We don't need to look at that one if we don't want to. Come on. There we go. New spreadsheet. Okay, so to pull this off on Excel, I need to know, so I'm just going to type at the top, I'm going to have N, I'm going to have X. So my N here is, what, 8? My X here is 6. And so then I'm just going to call this P hat. And P hat is X divided by N. Oops, I forgot to say equals X divided by N. Okay, so there's my estimate, right? Okay, so the next thing I need to do is I need to figure out what my z-score is. So to do that, I need to know my confidence level. And along with the confidence level, I'm going to get alpha. And I also need to know alpha over 2. Over 2. So what's my confidence level here? 90% or 0.9. Alpha is going to be 1 minus that. Oops, equals 1 minus that. And what's alpha over 2? Well, it's that over 2. Okay. So next thing I want to know on Excel, so it's the same calculation we were kind of writing down there. What is the critical z-score? I'm just going to call it z. And that is the inverse normal. No, normal inverse, right? Norm inverse. My probability is, I'm going to go for the alpha here, comma, 0, comma 1. So it's giving me the negative version of the z-score. So I need to be a little bit careful about that negative version. That can be a little tricky. So that's going to help me calculate the margin of error. The other part of the margin of error is that crazy square root. So to do the square root, I'm just going to go type, anybody remember the square root command? Yeah, SQRT. And then I just need to know what is p hat times parentheses 1 minus p hat. So I don't have to worry about screwing up the subtraction. And then dividing that by n. So I can just kind of point and click once I type those numbers in. So if anyone wants to try this in Excel later, you can watch this again. And it's the combination of these two numbers here that give me the margin of error. Now the negative z-score, I'm really not happy with that. So I'm going to stick a little negative sign in front of that, just to make it positive. So to calculate E, I multiply these two, oops, that's not me. There we go. To calculate E, I just multiply these two numbers together. So then my margin of error is the z-score times the funky square root. And that's that. Okay, so to 3 decimal places, it would be 0.252. So to get the left and right boundaries, I need to add and subtract that from p hat. Okay. So I'm just gonna call it p hat minus e on one side, and then I'll do p hat. If I didn't put the dash in there, then it looks like misspelled fat. And that, I guess we'll be looking at dash. So equals p hat minus e and p hat plus e. Did watching do this on Excel help you guys get a feel for what I'm calculating here? No, Shelby's not happy with this. We'll do another.
That is way more confusing than it needs to be.
Okay,
All of that.
that's all right. We're gonna do it again.
Like I
So,
get it on the calculator, but on that, like,
okay, well you got your
That's
calculator,
just-
so you're cool. You stick with your calculator. So what does this mean right here? So that's a 90% confidence level for the proportion of drivers that get annoyed by other drivers using their cell phones. My margin of error is over 25%. Now usually when we see margins of error, don't we want them to be littler numbers? Like wouldn't it be nice to have a 2% margin of error or 1% margin of error? Okay. So the only way, there's two ways to get a lower margin of error. One way is to lower your confidence level. If we went, like Michael said, for a 2% confidence level, or when I say 50%, sorry, I don't know, 2%. Yeah, 2% would be way too low. But 50% confidence level, that would shrink our margin of error. But are people going to listen to you if you say, hey, I'm 50% confident that this is true? Not really. The other way to shrink your confidence level is to raise your sample size. And we'll look later at how to figure that. What's a good sample size to start with? 8 is not. So we're going to look at another problem and we'll repeat these calculations.
Wait, so what does this mean? 100%?
Oh, what the hell does it mean? Yeah. Let's interpret it for my mother.
Poor person.
So I'm going to write this down in two different ways. So I am 90% confident that the scan pen. The proportion
You have the points.
well, go with it. You have a stutter when you write it.
take the square root of it, maybe. Let's just go with it. Let's see. I'm confident the proportion of annoyed drivers is between. What to be defined? I'm calling it 49.9 and 101. Is between 49.9% and 101%.
Well, that doesn't make any sense having 100 and
It doesn't, but that's what it came out. Okay, you can just call it 100% if you want.
okay.
I'm writing the number I calculated. Okay. Alternatively, instead of saying between, instead I could say is 0.75 plus or minus 0.25. If I went to 2 decimal places. I could state my point estimate in the middle plus or minus my margin of error.
Because they're totally going to know what that means.
How many times when you look at polls online do they say we estimate the proportion of people to be this? And then somewhere later they say the margin of error is that. That's more likely what you're going to see. So this won't necessarily be here. It'll be subtext in the bottom somewhere. So I estimate the proportion of people that are annoyed by drivers using cell phones is 75%. Little bottom script at the bottom will say, oh, by the way, my margin of error is 25%. People look at that and laugh. 25% margin of error is ridiculous. Do a new study.
Where did you get the 25?
That's what I count. So the 25, that's what we call the margin of error. And that's what I got when I found my z-score and multiplied by this square root, p hat, q hat, over n. So if you take your z-score, multiply by that square root, that's what we call the margin of error.
So it just happens, like it's not always going to be like 1 minus, because I thought for some reason we did like 1 minus 0.75.
Yeah, the q hat is always 1 minus p hat. Remember like P and Q for
Yeah.
binomials, right?
So it just happened that it was marginal error.
Oh, yes.
Just that well. Like,
That the margin of error happens to be Q hat.
Yeah.
That's total coincidence.
Okay.
Yeah.
So like, don't write that.
Yeah, don't write that down. Margin of error, yeah. If it was that easy, we wouldn't need all this.
Yeah, so I
stuff.
was like,
Yeah,
well,
like what
why
the hell are you
didn't
doing?
he
Yeah.
just do that?
Right. Totally different. Total coincidence. Just the way the numbers spell today. Is your phone okay?
Yeah.
Yeah.
Just rubbing it.
Rubbing his phone. All right, we're going to try a new problem. We're going to get to exercise all this math. So in my previous class, I had, how many people were there? There were 18 in my previous class. And how many people are here?
9.
Including me, there's 9. Let's include me. And in the previous class, I was counting how many females there were. In the previous class, I think it was 10. Is that right? I gotta look at my notes. I forgot. I was sure.
Where you get yourself to your body?
Well, it's who showed up today.
Really? Can you remember?
I can't remember for some reason. So let's see. 7.
I was really debating on not coming.
I'm so glad you came.
I didn't get home until like 5.
You seem a little tired.
A little bit.
Okay, let's see. This one is 10. Okay, and there were actually 18. Okay, so it's 10 out of 18. Okay, how many females do we have here? 1, 2, 3, 4, almost everybody, right? So there's
All the two.
all the 3.
Oh,
So I
yeah,
have,
think you-
so let's say I had 10,
1/3.
and now we have 6. So what's that give us? 27 versus 16. Okay. So we're going to make our calculation. P hat is going to be our estimate of the percent of female BMCC students. And I'm counting myself because I took yoga last term, so I'm a BMCC student. 2. So P hat here is 16 over 27, which we could approximate to several decimal places. Anybody?
0.59. Get more than that.
Yeah, give me one more.
2.
592?
Well, if I round it, it's 593.
593, okay, let's do that. So we're estimating that about 59.3% of BMCC students are female. So this is our point estimate. Of percent female BMCC students. So we have two kinds of estimates. We have point estimates and we have interval estimates. So we just finished off earlier with an interval estimate. So we're going to make an interval estimate here also. Because with an interval estimate, you can get a margin of error. Oops. Interval starts with an I, not an N. Let's try that again. So whenever you make an interval estimate, to start your interval, you need a center, and your center is whatever p hat is. So our p hat, which is 59.3 or 0.593, is our point estimate that's going to start our interval. Then our job next is to figure out what our margin of error is going to be to add to each side, subtract on the other side, to get my interval. So I need to find a lower bound and an upper bound on my interval, the left side and the right side. So we have to figure out what is the left side, what is the right side, and that's going to be based on the margin of error. Now, you can only do interval estimates if you decide on a confidence level. How confident do you want to be? I'll explain what a confidence level means shortly. Just need another example of interval estimates. Let's go for 90%, because we do. So we're going for 95% confidence level. that means alpha is 10%, and alpha over 2 is 5%. So we need to figure out what's called the critical z-score, z sub alpha over 2. What do you think our critical z-score is going to be here? Yeah, it's going to be the same number we had before. Now, sometimes they take z-scores up to 3 decimal points, so we're going to do that today. So we're going to call ours 1.644. How do we find that? So I just want to remind you, how do you find the critical number for confidence intervals? We're working with z-scores, so we put 0 in the middle. And then our confidence level goes in the middle, and we have 90% for confidence level. And that puts 5% in each tail. So then we have to do an inverse normal calculation on that. So one way to do it would be to do the inverse normal on 95%. Or you could do it on the 5% and be careful of your sign. What kind of curve did I just draw there?
This.
Yeah, a bell curve. That's a normal distribution, right? Z-scores, that's a normal distribution. Question though, when I'm trying to estimate percentage of females, what kind of situation is that?
Not normal.
So, no, it's not, really, it's not normal. I grab a person, I look, are you male or female? Well, I look at them, and I'm pretty good at telling, but just by looking, they're male or female. Thank you, Shelby.
And Elena and I work it. I could be in trouble.
So this is a binomial, right? Success means I found a female. Failure means I found a male. All right. So what makes it possible to replace a normal for a binomial? Because aren't they two totally different things?
They have the same curve.
Yeah, they could. Yeah, so sometimes you can approximate a binomial with a normal. And we have to go over right now when this is appropriate. So we're going to have a little side note, and I know Shelby's not happy about this, because I'm going to show her my pretty table again. Let's make that go away for a second. I'm going to use GeoGebra first. GeoGebra does a great job of drawing binomial distributions, so I'm just going to use GeoGebra. I just start typing BIN. It says, do you want a binomial distribution? I say yes. It says, how many trials? Well, each trial is a person I go up to. And so far, I've gone up to 27 people. Probability of a success. Okay, now this part's a little bit trickier. What's my probability of success? Well, here we're estimating the probability of success to be what? No, that's my confidence level. What's the probability I find a female based on my sample?
59.3.
59.3. So I'm going to go with that. So I'm going to type 0.593 and hit enter. So I just want to show you what this distribution looks like. Because we're mixing normals and binomials together, and that can sometimes be dangerous. Sometimes it's okay. Now, if I just showed you that right there, would you say that looks pretty damn normal?
Mm-hmm.
Isn't it nice and symmetric? Okay. So this thing has a range from 0 up to 27 over here. And it looks pretty bell-shaped. Do normals always look bell-shaped? The answer is no. Sometimes they look wicked skewed. This thing is slightly skewed. Can anybody tell which direction this thing is skewed to? Oops.
Looks towards the 27.
Yeah, so 27's right here, 0's right there, so there's a longer tail towards 0. The center of this distribution is x equals 593 again, times 27. Center of this distribution is right there at about 16. Is 16 exactly in the middle between 0 and 27? No, so it's skewed. Okay, this distribution is skewed. But even though it's skewed, we can still use a normal to approximate it. So next I'm going to draw a normal curve just to show you. Blow this up just a little. For a normal distribution, you need two parameters. What are they?
Mean standard deviation.
Yes, mean and standard deviation. So I'm going to ask GeoGebra to graph me a normal, normal, that first one, mean. What's the mean of this particular distribution? Well, it's about 16. That's what it is calculated. So I'm just going to type 16. How do you find standard deviation of a binomial? Anybody remember? Yeah, oh, n times p times q. Then what do you do with it?
Square root it.
Square root it, yeah. So I'm going to type standard deviation as SQRT of n, 27, times p, 0.593, times q, 0.407, I think.
Yeah.
Enter. Look at that. Does that normal sit right on top of that binomial?
Yes.
Almost bisecting the top of each column? Isn't that gorgeous? That's some good looking math. Come on. Can you see somebody getting that tattooed on the small of their back? All right, wouldn't that look nice?
Next tattoo right there.
All right. So there are times when we can't legitimately get away with replacing a normal distribution with a binomial distribution. Here is the rule. And we'll see if we pass. Does it look like we're going to pass the rule? I mean, doesn't that look pretty damn good?
Yeah.
Yes, it does. Okay, so I think we're going to pass the rule. Let's write the rule down before we can finish this. Rule. This is called a normal approximation of a binomial. And the rule is that n times p, your mean, has to be greater than 5, and n times q, that would be the mean of failing, has to also be greater than 5. Actually, I think they can go greater than or equal to. Yeah. So I was curious, what kinds of n's and p's satisfy this inequality? And that was that weird table that made Shelby unhappy. Let's look at it again. So across the top, I have a bunch of possible p's. And so I'm just going by 5%. 5, 10, 15, 20, 25, 30. Down the side, I have possible n's. Now, if we're using the central limit theorem, what do we think n should be?
Square.
Greater than 30? Central limit theorem? Yeah, greater than 30. Okay. So,
Unless it's normal.
Hold on.
yeah. So if we just picked on 30 as the marker, as a good sample size, then according to 30, that means these yellow ones are greater than 5. And if I scroll up to see what those yellow ones have to do with probabilities, that means if p is between 20 and 80%, you can use a sample size of 30. Now let's see, what's ours? Our sample size was 27. So here's the row for 27. And for 27, then you have to be in between. Oops. Row 28 is number 27. Yeah, sorry. That's confusing. So if I scroll up, it says for sample size of, it's still between 20 and 80% for sample size like 27. Often you have an estimate as to what p is. So for example, if somebody told me p is probably around 0.45, then that tells me my minimum sample size is 12, is what this table tells me. So either you have to fiddle with the inequalities or you have to look at a table to figure out what your sample size should be to estimate a particular proportion. And so this says minimum sample size of 12, I have 27, that's okay. Just this class on its own would not have been enough people to satisfy the requirements to use a normal distribution. Why the hell do I care about a normal distribution? Well, I care because I'm using z-scores. And z-scores come from normal distributions. So I can only do all of this if I think I can legitimately use a normal approximation to the measure. Pretty exciting. All right, so let's get busy. So next what we need to do is find our margin of error, now that we know we're on the right track. So the margin of error for a proportion call that E, and it's the critical z-score, z sub alpha over 2, times the square root of p hat times q hat over n, your sample size. So I would like you to figure out what our margin of error is here. And again, what's the important stuff? Our confidence level is 90%. And we found p hat to be 16 over 27. 27 being our sample size. So see if you can figure that out. We already know what z is, right? What's z here? 1.644. I'm going to go 3 decimal places. All right, so you calculate, I'll calculate, and let's hope we agree. Okay, so that's what I typed into the calculator. I did it all in one line, the inverse norm times the square root. And according to my calculator, I get a margin of error of 0.15553. So just for fun, I'm going to take it to 4 decimal places, so 0.1555. Now, if you round it along the way, you're going to have a slightly different answer. So I'm going to do this with some rounding just to compare. So let's crack 5. Okay, so I have almost no rounding error there. If I had rounded p hat to 3 decimal places, like what were we calling it before? 0.593?
Mm-hmm.
Okay. So I decided to use fractions instead, so I didn't have to worry about rounding.
Oh, that's what threw me off.
So if I went 1.644, there's some rounding, right? So the problem is you want to be careful with introducing too much rounding error. And so then I'm going to multiply by the square root of 0.593 times q hat, which is what? 0.407. And then divide that by 27. Oops, I guess not. Parentheses on this calculator. And enter. So another possible one is 0.1554. Notice I rounded twice there, so I have a little bit of rounding error. If you anybody calculate the square root separately here, and then multiply by the z-score? Yeah, so if you do that, you're going to have a slightly different answer again. So you do want to be careful. Sometimes on the homework problems, it gets a little picky. So another possible answer. So if I were to round this to 3 decimal places and call it 0.0946, you didn't? Uh-oh. We've got to get these calculations down. 0.0946 times 1.644. So that gives me, yeah, that's closer to my other one, actually. I'm kind of lucky there. Yeah. So is there a lot of room for rounding error and finding a margin of error?
Yes.
Yeah, there is. So you got to be careful. It's possible if you keep it in fraction form that you can just type inverse norm times square root, fraction, fraction, divide by 27. And then you don't have to worry about rounding. The computer just does its rounding at the end. Will the homework be super picky about it? Usually we're going to want to be within 3 decimal places. And so all these three calculations I just did were within 3 decimal places of each other. So that was okay. Okay, so next we need to finish this and state what it means.
Oh, it's wrong.
What? You have a problem?
It was 0.1555. I got 0.155.
Okay, so you're close. Yeah, you're in the ballpark. That's good.
Gold star.
All right.
It makes me happy to do that.
So I'm just going to draw a picture of what we found. We are estimating the proportion of female students to be 0.593. Right? That's what we call p-hat. We just calculate our margin of error to be about 0.155. I'm calling it 555, just for the help of it. Usually I would go 3 decimal places for both, but if I add those together, right, my center plus my margin of error, that takes me out to the right. What's that going to give me? That's going to give me 5, 8, 4, is that right? 0.7485-ish.
Yeah.
And then subtracting on the other side, so I want to go minus E on this side. And I don't know if I'm ready to do that one in my head. Somebody help me out there.
0.4375.
So we're estimating that the percent, so here's my conclusion here. I am 90% confident that the percent of BMCC students that are female is between 0.4375 and 0.7485. My mother would say, "What? I don't like those numbers." I say, "Okay, Mom, about 43.75% and 74.85%. And she'd be like, "Oh, okay, that's fine, Gary. See you later." But my stepdad would be listening, and he'd say, "So what do you mean by 90% confident? What the hell does that mean?" Was what he'd say to me. What the hell does 90% confident mean? Here's what it does not mean. It does not mean that there's a 90% chance that the actual percentage is in that interval. It does not mean that. What it means is if I did a whole bunch of random samples of size 27, a whole bunch of them, about 90% of those samples would make similar intervals that would actually contain the real proportion. Subtle distinction. 90% of similar samples will lead to intervals that contain the real proportion. 90% of similar samples. My mother really doesn't want to hear this, but we need to know it. 90% of similar samples will lead to intervals containing the actual proportion. So I'm going to draw a picture of what that means. So that means like if I did a lot of different samples of size 27, so let's say I did 10 of them. Okay, is that a lot according to the law of large numbers? No way, but I'm just going to do 10 anyway. So somewhere out in space lives the actual percentage, and I just did an interval, and let's say mine happens to be one of those 90%. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 of them. 90% would be 9 out of 10, right? Yeah, so on average, 9 out of 10 of similar samples will lead to intervals containing the actual proportion. Does it mean my interval has a 90% chance of being one of them? No. It doesn't. It doesn't mean proportion. Takes some getting used to, but I do need you to know that interpretation. Very important you read section 7.2 in the book. So let's see. What's our margin of error here? 15.5%. Would you say that's a small margin of error or a large margin of error? That's a large margin of error, right? People are going to laugh at me. 15%, that's useless, right? So, what can I do to lower the margin of error? There's two things I can do. Anybody remember?
Raise your
Increase the sample size.
Increase the sample size. That's really the big one. Or I could lower my confidence level. I could go for like a 50 or 80% confidence level, which would be kind of useless also. So the big thing is to raise the sample size. So let's take a look at that. Margin of error for proportions look like this. You have your crazy z-score related to your confidence level times your p-hat times your q-hat divided by n. So let's just stick with a particular confidence level. Let's stick with 90% because we've been messing with it. So if I have a confidence level of 90%, that means z is going to be about that 1.644 number. So we're going to stick with that. Now, I would like a better margin of error. What would we like for a margin of error? Shelby? 5%? Shelby? That'll work too. Okay, let's go for a 5% margin of error. Okay. So we want E to be, what's that? Close to 0, right? We can't go with 0%. So we might even go lower than 5%. Should we be daring? Or just stick with 5?
Well, I'm actually Michael, not Gary.
Okay, so Michael says we're going to stick with 5. Forget about daring. Okay, so we're going to go 5%. So that means we get this equation. 5% equals the z-score, 1.644, times the square root of p-hat times q-hat over n. Okay. Now, usually we put p and q in there, but we don't know p and q. We're trying to find it. If I haven't done any samples yet, I don't even have a guess at p-hat and q-hat. We have a guess, don't we? Our p-hat was 0.593. What do you do if you have no clue what p-hat should be?
1.
Almost, 0.5. Yeah, you let p-hat be 0.5.
Oh, I was thinking both of them be 1 together.
Both of them be 1. Well, remember, q-hat is always 1 minus p-hat.
Yeah.
So if you chose 1 for p-hat, q is 0, and then you're dead. So usually 0.5 is what people go for. Let's just go for 0.5. It's in the middle. Okay. But we have a better idea. We're going to go with that 0.539. Unless you're 593. Or do you think that number sucks? Because I only had 27 people.
27 better than our 9.
The 27 was better than 9, and 27 is okay in that normal approximation of a binomial.
And isn't it better than a guess anyway?
It's better than just a guess, right? Even if it's a convenience sample, I think it's better than a guess, yeah. So we're going to go with that. So now we have more information to put in here. Instead of p-hat and q-hat, we're going to put in those other numbers we have, which are 0.593 times 0.407 over n. So all we have to do is solve that for n. So let's just do that together. Okay, so let me see. If I want to solve for n, I want to put this number on the other side first. So how do I get that number on the other side? What? Divide, yeah. It's connected to multiplication, by multiplication, so we divide. So 5% I really should write as a decimal, 0.05. I need to divide it by 1.644. I'm not going to round yet. I'm just going to carry this stuff around. So now on the other side, I have the square root of p-hat, q-hat over n. So 0.593, 0.407 over n. What am I going to do next to try and solve for it? I got to get rid of that square root. How do I get rid of that? Yeah, square both sides. So we'll square this side. Squaring this side will kill the root. So now I have 0.05 over 1.644 squared equals p hat, oops, digit in there, times q hat over n. Okay, any tips, algebra? There's a lot of ways we can go here algebraically. Any ideas? I don't particularly like where n is in the bottom.
One over the other side.
Oh, flip both sides? Yeah, I could flip both sides. Now, instead of writing 1 over that, I could just call it 1.644 over 0.05. And then if I flip this side, that gives me n over 0.593. Excellent suggestion.
Yeah, let me say.
On order,
Square.
squared, thank you. Okay. Last step, pretty much.
Bless you, by the way.
Yeah, times.
Yeah, multiply those two numbers out of the denominator. So finally, I'm going to get this crazy fraction, 1.644 squared times p hat times q hat. 0.593, 0.407, and that is our estimate of our sample size if we want a 5% margin of error. Whew. There's a formula for this. We just derived it. Oh, let's see. What the hell do we get? Okay, so parentheses, my z-score divided by the margin of error I wish for, parentheses close, squared, times p hat, 0.593, times q hat, 0.407, and I get 261 is the ideal sample size to estimate this particular population percentage with a margin of error of about 5%.
Well, we don't have that.
No, so we have to walk around campus and get a random sample of about 261 or higher, is what we just found. So if we think that's within our means to do, then we go for it. If not, then we have to modify our confidence level and or our margin of error that's accepted. And this is what statisticians have to do to try and figure out how many people to sample to estimate something. And we have to balance the sample size, the confidence level, and the margin of error. All those three things are interrelated. Is there a sure way to just pick it and go? No. You have to balance. You may decide you really want a 1% margin of error. What would happen if I went for a 1% margin of error? Well, I would just replace the 0.5 with the 0.05 with a 0.01. Oh, why not? Let's try it. So I just go second enter on the calculator. I'm just going to go back and put a 1 instead of that 5. And I would have to interview, hey, 6,524 people. I'm not going to go for a 1% margin of error. I can handle 261 people. I don't think I want to do 6,523. So it's got to be some kind of balance. All right, so let's look at this formula. And I'm going to try and break it down. And then we are out of time for fun with this beautiful stuff. Okay, so here's the formula they gave us. The n is 261. So where did the 1.644 come from? That was my z-score. What is the 0.05? Where'd that come from? That's E, the margin of error. Yeah, excellent. Right on top of this. What was the 0.593? Oh, and then I have to square this stuff, right? That's my p hat, and this is my q hat. That's not too bad. That's the formula for estimating a sample size. based on your margin of error and your confidence level. So usually it's written a little bit different. I could square the top and the bottom, so that would give me a z squared. And I'm just going to say that's times p hat times q hat over the margin of error squared. This is the way the book presents it. There's lots of different ways to write it. But that's one way of approximating how many people you should sample to get the margin of error you like with the confidence level you like. That's the most algebra we've done all term. You don't feel good now? All right, so let me just point out where we are. What we're doing here is playing in section 7.2, which is about confidence intervals for proportions. We're going to skip 7.3 because it's just not all that useful, and do 7.4 next. But we have a bit of work to do to get used to this stuff. So that'll take most of the next class. We may start 7.4 in the next class. We'll see how it goes. So the goal is to finish section 7.2 and 4, and then 8. I think it's 8.2 and 4 also. We're only going to do 2 sections in each chapter. I would love to do section 9.2, but I seriously doubt we'll get there. I posted homework for 7.2 for now.
So we've got 4 sections left over.
We have 4 sections left total.